In this video, we're going to look at complex numbers. We're going to define what they are, and then we're going to perform operations with complex numbers. So the first thing we want to do is to define a complex number. But to define the complex number, we also have to define this imaginary unit. Now, it is defined as the square root of -1, but equally important, I need to know that I squared is -1. This is a little confusing for some people because they've, in arithmetic, heard so many times that there's no way to get a negative if you square a number. But there is, but it takes the imaginary unit. Now, the set of all numbers in the form a plus bi, with a and b both being real numbers and the imaginary unit being I, those are my complex numbers. That is the set of all complex numbers, a plus bi. And a plus bi is the standard form for a complex number. So when you give an answer, we don't want it to look like 1 plus 2i over 3 because that's not standard form. Standard form is going to be 1 over 3 plus 2 over 3i. The form of a complex number, a plus bi, is like a binomial, a plus bx. It's written kind of backwards, but it works very much the same. To add, subtract, and multiply complex numbers, we use the exact same methods that we used for binomials. So let's add and subtract the complex numbers. Note the parentheses here are denoting the fact that these are two complex numbers. It's not 4 terms, it's 2 numbers. But I treat it like a binomial plus a binomial, where we add the like terms. So I'm going to say the real part, 5 plus 3, plus the imaginary parts. That was a minus 2i, so I'm going to look at it as a negative 2i, plus a positive 3i. And then my answer for adding those is just 8 plus I, because -2 plus 3 is positive 1. The same story with subtraction, but let me give you a word of caution again. That's a minus sign in front of parentheses. Many students will forget that it must be distributed. So you've either got to hit it twice or distribute it, whichever way you want to look at it. But my real part is going to be 2 minus 12. Most people don't miss that one. But my complex part is going to be 6i minus -i. The minus sign and the negative sign comes from the minus inside parentheses. So my correct answer is -10 plus 7i. And that is a complex number with a real and imaginary part. Multiplying is also going to work like binomials, but it's going to have a little bit of a twist to it. First of all, this is a monomial times a binomial look, and it works the same way. I merely distribute the 7i through. So that's going to be 7i times 2 minus 7i times 9i. So that's going to be 14i minus 63i squared. Here's the catch. You can't leave an I square. So I've got to go back to my definition and turn that I squared into a -1. So that's going to leave me with 14i minus a negative, which is plus positive 63. Now, I still don't want to leave this as my final answer because it's not in standard form. So I do want to swing it around and put the real part in the front plus the complex part with the imaginary part with the imaginary number in the back. That's standard form for a complex number. Okay, and the last example on this page, it's a FOIL problem if it's two binomials. So I'm going to do it the same way. My first multiplied together, 5 times 6 is 30. My outer, 5 times negative 3i is minus 15i. Again, that was my outer. My inner, 4 times 6 is 24, so 24i plus 24i. And my last, 4 times negative 3 is negative 12, so that's negative 12i squared. But watch this, because this is kind of cool. That's going to be 30. I'm still going to collect my outer and inner terms. 24 minus 15, I believe, is 9. But look at this. I squared is negative 1. Negative 12 times negative 1 is a plus 12. And I still have like terms. So my answer is 42 plus 9i. Still a complex number in standard form with the real part plus the imaginary part. Before we attempt division, we need to be sure that we define something else here, and that is a complex conjugate. For the complex number a plus bi, we define its complex conjugate to be a minus bi. The conjugate is the same as the conjugate with radicals. It's just this time we're dealing with imaginary parts. So the product of a complex number and its conjugate is a real number because conjugate pairs give the difference of squares. So that's going to be a squared minus bi squared. So notice that's a squared minus b squared, I squared. But I squared is negative 1, and negative 1 times negative b squared is a positive b squared. Note, no i's, no imaginary units in there. This is a real number, and it's that sum of squares that we said we could never factor. Now that you know what a complex conjugate is, let's talk about division. The goal of complex number division is to obtain a real number in the denominator. We do not want any imaginary units showing up in the denominator. So to do that, we're going to multiply numerator and denominator by the conjugate of the denominator, because the conjugate pairs is the difference of squares, and we just saw that that's going to be a real number. So to divide complex numbers, we're going to use conjugates. A quick example of division before I let you go. Divide and express the result in standard form. So to divide, fraction bar means divided by. To divide, I'm going to multiply by, if I can, 1 in the form of the conjugate of the denominator over itself. Okay? That's how I'm going to divide. I'm going to multiply by the conjugate of the denominator over itself. Now the numerator, that's going to need a FOIL. So first, 3 times 4 is 12, plus outer, 3 times I is 3i, plus inner, 2i times 4 is 8i, plus last 2i times I is 2i squared. But again, I squared is negative 1, so he's going to change the sign there. And conjugate pairs gives the difference of squares. 4 squared is 16 minus I squared, but I squared is negative 1. So he's going to be added there. Let's collect like terms. 12 plus negative 2 is 10. Plus 3 plus 8 is 11 i's. Over 16 plus 1 minus negative, same as plus positive, is 17. This is not standard form because standard form says I have two parts. I have a real part, 10 over 17, plus I have an imaginary part, 11 over 17 i's. This should remind you of rationalizing the denominator with radicals because it is exactly the same process.